Let's start with the introduction of Green's theorem. The creator is George Green, 1828, a self-taught English mathematician who ran his family's grain mill. The purpose developed is to solve complex problems and gravitational and electrostatic potential field. And the discovery, originally published in isolation, popularized years later by a young William Thomson. Green's theorem established a relationship between a line integral around simple closed curve and double integral over the plane region bounded by that curve. There are two forms of Green's theorem, which are the circulation form and the divergence form. The first one is circulation form. Let C be a positive-oriented, simple and curved, and let D be the region bounded by C. If Psy and Qsy have continuous partial derivative, left-hand side measures circulation along the boundary C and the right-hand side measures total rotation inside region D. For the second one is divergence form. Green's theorem can also describe flux across a boundary. For vector field F equal to Fq, the left-hand side is line integral, which is net outward flux across boundary C, and right-hand side is double integral, which is total divergence inside D. Next, move to the condition when Green's theorem is applicable. For the first one is if it is simple closed curve C, which means it starts and ends at the same point. The second is positive orientation, counterclockwise direction, and region D stays on the left. Third is piecewise smooth curve, smooth section and no breaks. And lastly, continuity condition, which is Psy and Qsy have continuous partial derivative. However, Green's theorem is not applicable if the curve is open because the path does not enclose a region D, and also a self-intersecting curve such as a figure 8 path make it discontinuities and singularities within the region D. Then be directly applied to region with host unless the theorem is modified by considering the inner boundaries or introducing suitable cuts.
First, we take a look at question 1. We need to verify Green's theorem for f as y equals to x squared plus y squared plus 5xy, and C is the boundary of the region enclosed by y equals to x squared and y equals to 8, oriented anti-clockwise. First, let's solve the right-hand side, which is the double integral over the enclosed region. From the graph, the region is bounded by the parabola y equals to x squared and the horizontal line y equals to 8. By substituting y equals to 8 into the parabola, we obtain that x equals to plus minus 2 square root 2, which gives the limits of integration. From the vector field, we compute that del q over del x equals to 5y and del p over del y equals to 2y. Therefore, del q over del x minus del p over del y equals to 3y. We substitute this into the Green's theorem and evaluate the double integral over the given region. Next, we evaluate the integral. First, we integrate with respect to y and then with respect to x. After simplifying and substituting the upper and lower limits, we obtain the numerical value is 434.4. So the value of the right-hand side of Green's theorem is 434.4. Now let's calculate the left-hand side, which is the line integral around the closed curve. The boundary consists of two curves, which is C1 is the parabola y equals to x squared, and C2 is the horizontal line y equals to 8. Since the curve is enclosed, the total line integral is the sum of the integral over these two paths. We will calculate each curve separately before adding the result together. First, we evaluate the integral along the curve C1. We parameterize the curve as x equals to t and y equals to t squared, where the t range from negative 2 square root 2 to 2 square root 2. then dx will equals to dt, dy will equals to 2t dt. After substituting this expression into the line integral and simplifying, we integrate over the given interval. The result for curve C1 is 811.6. Next, we calculate the integral along the curve C2. Here the curve is horizontal line, which is y equals to 8, so dy equals to 0. We parameterize it as x equal to t and y equals to 8. Because the orientation is from the right to left, the limits are from 2 square root of 2 to negative 2 square root of 2. Substituting this value into the line integral and evaluating gives negative 377.2. This is the contribution for the second curve. Finally, we add the result from both curves. The first curve gives 811.6 and the second curve gives negative 377.2. Therefore, 811.6 plus negative 377.2 will equals to 434.4. This matches the value obtained from the double integral on the right hand side. Since both integrals are equals, we have successfully verified the Green's theorem for this vector field.
For question 2, we are given a vector field f of xy equals x plus y squared I plus 2x minus yj, and we are asked to evaluate the line integral of f dot dr. This question has two parts, which is part A, evaluate it directly. This means we will parameterize the curve, substitute x and y into the vector field, and then integrate f dot dr along the path. For part B, evaluate using the Green's theorem method. Green's theorems allow us to convert the line integral around a closed curve into a double integral over the region D. The formula is the double integral of dq over dx minus dp over dy dA, where p is the I component and q is the j component. By comparing both methods, you can verify that the results are the same. For part A, we will evaluate the line integral directly. From the graph on the right, the closed curve C is made up of three parts, which is C1, C2, and also C3. The vector field is given as P equals to x plus y squared and Q equals to 2x minus y. On this slide, we will show the working for C1, which is y equals to x squared from x equals to 0 to x equals to 1. To parameterize, we let x equals to t and y equals to 2 squared, where t goes from 0 to 1. Then dx equals to dt and dy equals to 2t dt. Next, we substitute into the integration of p dx plus q dy. This becomes the integral from 0 to 1 of t plus t to the power of 4 and 2t minus t squared times with 2t dt. After simplifying, we get the integral of t plus t to the power of 4 plus 4t to the power of 2 minus 2t to the power of 3 dt. Solving this gives us negative 23 over 15 for C1. Next, we continue with the direct method for C2 and C3. For C2, x equals to 1, where y goes from 1 to 2. We set y equals to t and x equals to 1. So, dx equals to 0 and dy equals to dt. Substituting p and q into the integral of p dx plus q dy, the first part becomes 0. After integrating from 1 to 2, we get 1 over 2 for C2. Meanwhile, for C3, y equals to 2x, where x goes from 1 to 0. Then we let x equals to t and y equals to 2t. So dx equals to dt and dy equals to 2 dt. Substituting into p and q give us the integral of t plus 4t to the power of 2 dt from 1 to 0. Solving this, we get negative 11 over 6 for C3. Finally, the total line integral is the sum of all three parts. From the previous slide, C1 was negative 23 over 15, so negative 23 over 15 plus 1 over 2 minus 11 over 6 equals to 1 over 5. Therefore, the value of the line integral by direct method is 1 over 5. Now, for part B, we verify the answer using Green's theorem. Green's theorem states that the line integral around a closed curve C is equal to double integral over region D of dq over dx minus dp over dy dA. From the equation, we have p equals to x plus y squared and q equals to 2x minus y. So dq over dx equals to 2 and dp over dy equals to 2y. Therefore, dq over dx minus dp over dy equals to 2 minus 2y. From the graph earlier, the limits for region D are x from 0 to 1 and y from x squared to 2x. So we set up the double integral from 0 to 1 and y equals to x squared to 2x of 2 minus 2x dy dx. After integrating with respect to y, then x, we simplify to the integral of 4x minus 6x to the power of 2 plus x to the power of 4 dx from 0 to 1. Solving this gives us 2x to the power of 2 minus 2x to the power of 3 plus x to the power of 5 over 5 from 0 to 1, which is equals to 1 over 5. The final answer is 1 over 5. So, therefore, we can conclude that this matches our direct method, so the answer is verified.
Here are the maple comment and output for question 1.
This slide shows the maple solver verification for question 2. The comments and output from maple confirm the result we obtained earlier by hand. Therefore, the manual calculation and the maple calculation are consistent.